I just want to take a moment now before we really get started to introduce the team that helped put this together. This has been a great effort from everyone involved, starting with Theresa Alexander here at the front. Yours truly here, Andrew Lauziere, Hadi Vafaei up at the front, Anshuman Swain here in the center, Hao Yiu over here also in the front, and Chelsea Haakenson at the front as well. We all kind of pulled over the course of the past couple weeks to create materials, build these slides, and organize everything to try to pack as much as possible as you can get in just a 2-hour window. And we think it'll be a great kind of kickoff for each of you, no matter which part of in the statistical modeling machine learning game, whichever rung you're at. This is going to be a foundation or maybe improve things a little bit. But either way, everybody now has the ball rolling, if you will. Everybody has taken their first step. So here's an outline of our agenda. I'm going to be giving a quick lecture on just kind of the basics of statistics, statistical learning, a little bit of philosophy about the scientific method and where does statistical modeling actually fit in this pipeline. From there, I'm going to hand it off to Hao and Theresa, who are going to talk about the kind of most fundamental problem in statistical modeling, which is regressions. This is where you're modeling, we call it real valued output. From there, we're going to have our first hands-on coding session, and we'll have a link for you to download either the R code or the Python code. You'll be running it on a cloud server, so there's no issues with having the right data, having the right versions. You'll all be able to just run it, whichever one you prefer, on your machine, but on the cloud, so it's very smooth. Then we'll segue into the second lecture, where we deal with classification problems, right? This is kind of the difference. Instead of predicting a real number, we want to predict a label. Say either a yes, no, a true, false, high or low, and so on. Followed by then another hands-on lecture where we're going to apply the topics that we discuss in the classification section. And then for the last 30 minutes of this workshop, we're just going to have a very open, informal question and answer session where the leads will be up here, moving around, whether working one-on-one or answering questions up here if people have larger questions. So let's get right into it. So we picked a data set today so that everybody is kind of now working together, and this is just a small colleges data set, right? So we have data on about 770 United States colleges and universities. Now there's about 5,000 or so when I Googled it a few days ago. So what we have here is a sample, right? We have a sample of colleges from the kind of greater population, which would be all colleges and universities in the country. And our goal, right, is using this data, can we learn some things about colleges and universities in this country? So what I'm going to implore you all here to do today is going to try to imagine yourselves in the shoes of, say, a researcher who is interested in answering some questions regarding data about colleges and universities. So what we have here in a standard matrix format, or what we'll see in R, Python, or this idea of a data frame, is we have on each row a different college or university, and on columns we have different variables, or kind of some measured characteristic of that college. And so the first one we see is just the college name. Then we see whether private, which would be a binary or labeled variable for yes or no, whether it's private, and if it's not private, then it's public. We see the number of applications, number of accepted, number of enrolled, and then the top 10 and 25% numbers refer to, of these students who are admitted, how many of them come from, say, which percentage come from the top 10 or 25%. F and P, undergrad, refer to the number of full and part-time undergrad students. Out of state is intuitive as well, number of out-of-state students. Room and board and books, personal, those are all costs, so in a US dollar amount. This PhD variable refers to the percentage of faculty at the university or college that hold a PhD. Terminal would be how many of those faculty and staff also have terminal degrees. Student-faculty ratio, right? It's something that we keep in mind a lot. We're going to be looking at that variable a lot today. Percent alumni is the percentage of alumni that donate. Expend would be the total expenditure the average student has there. And grad rate, right, is the percentage of students that graduate. So I know it's a mouthful, a lot of features, but most of them are pretty intuitive, and we figured it's something that everyone can kind of identify with on at least some level, since we were all at the University of Maryland, a college, university. And so now that we are we have a data set, we have a task, I want to kind of talk about why it is, statistical modeling is useful in a sense, or why we actually want to learn these techniques, why there's a demand for these techniques at all. And in a sense, I like to relate it back to the scientific method. And I'm aware that we have a wide range of students here today, ranging from some of the biological sciences, where you probably have much more hands-on experience practicing and studying the scientific method, through engineering, mathematics, computer science. I believe we have some from animal sciences, all across the board. And so I want to unify everyone through this framework. And in statistics, we really are focusing on this idea of the hypothesis, experiment, and analysis. Right? So your hypothesis is, in a sense, some prediction or assumption about reality. Right? And you perform an experiment with data and then analyze it via a statistical model to kind of build evidence, in a sense, or assess the evidence in the data to then come to a conclusion. So in every bit of research, well, I'd imagine the vast majority of research, this is kind of what you see, right? You see some proposed phenomena, some people gather data, you try to build a model based on this hypothesis, and then you look at the actual output of the model, you analyze it, and argue whether or not there's evidence to reject this hypothesis about reality or not. And so this part here, this analysis, right, this is our statistical modeling. This is how do we actually use the data to build something that we can try to turn some information or data into a type of knowledge, something to discuss, evidence to kind of either support our reality or show that whatever our hypothesis was does not fit given the data we've gathered. So now we're going to kind of pull through with some actual charts here from the data itself. So this first introductory chart, we have on the x-axis the student-faculty ratio for just a subset of all the colleges. So we see we're going from 0 to 10% student-faculty ratio. And then on the y-axis, we have the graduation rate. Again, you see it's ranging from 30 to 100%. Imagine none of us would really want to be at a school that has a college with less than a 30% graduation rate. Your odds not in your favor, as the 8-ball says. So, looking at this, right, the idea is, do we observe some sort of relationship? Is there some way to understand how student-faculty ratio could directly relate to graduation rates? And just looking at this kind of blotch, right, it doesn't really look so strong. But what we're gonna talk about is kind of how we can look at different models to assess this problem, build different models with different assumptions that are stronger or weaker in different scenarios. But before that, we need to talk about this overarching kind of like the topology for all my math people in the audience of these modeling tasks. Right? So within kind of machine learning or statistical learning, for the sake of this workshop, we're just going to kind of use them interchangeably. Some more purists may argue one means this, one means that, but that's a little bit beyond the scope here. But so within kind of this greater umbrella of tasks, we have what are called supervised learning tasks and unsupervised learning tasks. So the one before where we had some supervision, or let's say the actual graduation rate, and we want to use some other independent variables to predict this dependent variable, the graduation rate, that's a supervised learning task. You can imagine it, there is the true answer is known. Right? We have we have data that's gathered where our kind of outcome of interest has been captured as well. So now we're looking to kind of build the relationship between these inputs to the output. Is there something there? And these are the types of problems we're really going to be discussing today, right? As we mentioned earlier with regression versus classification problems, and that is a distinction between the type of output you're trying to model. Unsupervised learning problems are a very hot field of study, and I wish we had more time to get into those today. But the reason why that's so important to understand unsupervised learning methods is because the vast, vast majority of the data in the world that exists is what we call unlabeled, or it's gathered, but there is no kind of association of truth with it. Right? So a way to think about this is, we have, say, some image scans of patients, tons of them across the world. When people go into hospitals, right, they get this data gathered about themselves, but there often isn't some professional that can, pinpoint, say, yes, there is some cancerous lesion or so in this person, right? Most of the data, because it takes effort, it takes a professional to go through and what we call annotate or provide labels or provide ground truth for data. It's oftentimes very expensive because you're using professionals. It's very time consuming. And for a lot of research, this is the main clog in the pipeline, or the hump that slows so many people down, is getting good labeled data. So while unsupervised learning is very important, we're going to focus on supervised learning today. So looking back at our first plot, we have on the left, if we were to try to model this as a regression task, right? So each kind of blue point here you can imagine is just this XY plot of two-dimensional of just the student-faculty ratio and the corresponding graduation rate. And ideally, we want to fit some curve or line, some functional form that models it well. It looks a little daunting, and we'll see just how daunting it is soon. But for now, we're just looking at it as a kind of hypothetical. Then on the classification side, right, we can split our data into, say, a high and low graduation school. And we're going to do this in the hands-on portion as well. We pick a threshold. We say if it's above a 65% graduation rate, then it's a high graduation school. If it's below 65% graduation rate, then it's a low graduation school. Now, while this seems a bit arbitrary, right, we just kind of pick 65, we're doing it mostly to illustrate the point while keeping it concise. Oftentimes, whether it's say in cancer diagnosis or something where you have some data about a patient, you want to predict like a positive or negative for their diagnosis, or in say the self-driving car, when you're trying to, you detect some object and you want to say whether or not it's a pedestrian, right? These are kind of more realistic examples of classification tasks. However, for our case, just to illustrate the difference between these two types of problems, we pick a cutoff. But you can naturally see how any regression task can kind of be turned into a classification task, depending on, if you have some, more methodological reason as to why, say, 65 is the right cutoff. So the big thing that we're going to harp on today, and it's, if you learn nothing else from this, I would really hope that you learn kind of this difference between overfitting and underfitting models, which is also known as this trade-off between flexibility and interpretability, capacity in the model. Right? So you could imagine the most simple model, which would just be, say, a straight line, right? If we make an assumption that the relationship between student-faculty ratio and graduation rate is some sort of line, like, a y equals mx plus b line, it's no more loaded terminology than that. This is what the line of best fit gives us for this data. And we can all kind of look and see that this isn't really quite capturing the relationship as it exists. There's a lot of error, and it doesn't really seem to get any of them particularly right, except maybe that a few blue points that are kind of close to the line. But what if we say we want a more complicated model? So we add more flexibility into the model, right? So as you progress from a line, which we'd say is a first degree polynomial, to say a quadratic, which is a second, or a cubic, a third, all the way to a fourth degree, this is what the fit looks like. And it looks a little bit better, but at the same time, do we really believe that this is the relationship, right? I mean, in a sense, what we really are trying to ascertain through this process is we want to understand the relationship between these variables. How is it that changes in one affects the other? And this model also doesn't really look too strong. I mean, perhaps we need more data. Oftentimes, gathering more data helps smooth a lot of things over. But if we go all the way now to the nth extreme, we're already at the first extreme, say a degree 1 to a degree 15, we can see how closely it's fitting the points. And this is a phenomenon we would call overfitting, or our model is kind of too powerful to fit this data. And so you can see how it very closely tries to go through the points, almost like a connect the dots type fashion. An interesting fact is if you have, say, n points, you can perfectly fit all of them with an n-1 degree polynomial. So theoretically, if we had, I believe there's, say, like 30 points here, if we had a 29 degree polynomial, we'd see it literally go through every single point. But what does that tell us, right? That doesn't actually help us with anything. Sure, it looks like on our on our training data here, or this subset, our sample that we observe, that it's powerful, but it's not going to what we call generalize well to unseen data, right? It kind of is just almost too glued onto our sample. Why would it, we don't have any reason to expect that it would do well on future data, unseen data. If you want to apply your model based on your sample to data out, when you gather it again. So what's the right answer here? Do we want underfitting, which is kind of a simple model, which is easier to interpret, but doesn't quite capture the relationships? No. An overfit model, which can be very difficult to interpret, but looks good on paper, at least on the training data? No. Obviously, the answer is kind of finding that sweet spot in the middle. And that's really the art of the whole thing. And the more, as you learn this, you can sell it as an art and as a skill, the more you kind of up your self-worth as you're doing these tasks, out in the real world, you can kind of argue for more money because you have that touch. So part of the practice here is kind of getting that touch. So here's the last thing of our introduction we're going to talk about with this overfitting, underfitting. This is different data, just so you know, but to illustrate this point. So if we're comparing three models here, right, and we can see going left to right, there's incrementally stronger fits, right, a more powerful model. And we see on the top row, when it's kind of the model is what we say learned or fit on training data, our sample, versus then how it's applied to unseen data. So a common practice in statistics or machine learning is to take all the data you gather, kind of split it, usually like an 80-20, into two different sets, what we call a training set, which you use to build your model, to train it to fit it, if you will. And then this test set that's held out to evaluate your model. One of the key assumptions in statistical modeling is that our data comes from a random sample. They're all independent. So we have reason to believe that, if we train a model on this 80% that's randomly pulled from our random sample, if it does well on this bit that's held out, then that's evidence to suggest that it would also generalize well to data that we haven't even gathered yet. So we want a model that simultaneously kind of explains the phenomena at hand. It's a model of reality. It fits well. But we also want it to generalize to unseen data. And as we saw with the high overfit model before, we could have a model that fits our sample data very well, but then doesn't generalize. It's useless. So finding the sweet spot here, and if you look at this curve then on the bottom, right, you see that as your model complexity or capacity increases, your error goes down for your training data, right? Because we had this high overfit model that could perfectly capture the relationship in the sample data, but then when we see the test error for the held out data, or as we see in this bottom right graph here, it does absolutely poorly. Because it's almost like it's learned to do one thing really well, but then once it sees something even slightly different, it falls apart. So where do we want? We want this sweet spot here. We want that good model, right where that kind of points 2 and 5 are, where we minimize the test error. It's something that we believe will be useful outside the data we gathered, so long as other data look similar to that of our sample. This is a phenomenon known as having a sample that is representative. And this gets more into kind of how do you gather good data, which is a little bit beyond the scope of this, but it's something that you always have to keep in mind. So now we've established some of the basics. I'm going to hand it off to Theresa and Hao, who are going to talk more in depth about regression.
So as Andrew mentioned before, we have two basic classes of model types. We have our regressions and our classifications. So remember, regression is when we're looking at problems where we have a continuous outcome. So we're looking at something that's on a range of numerical values that we want to predict what our outcome would be. So we're going to use this example throughout the regression examples. So here we're going to use graduation rate as our outcome variable. So this is the percentage of people who graduate going into these colleges. This is a histogram of all the different colleges. So so we've colored them by their quantiles. So you can see that the lower 25%, we don't have a whole ton of colleges that have graduation rates in the lower 25%, and we have a whole ton of colleges in between 50 and 75% graduation rate. So with that, does anyone see anything glaringly wrong with this histogram? Considering we're looking at graduation rate as a percentage.
More than 100.
Yeah, right. So how's that happen? We have a college here that has 120% graduation rate, which obviously is not possible. So there's been some kind of recording error here, which just goes to show, even if you're the one collecting the data, there's going to be errors in your data. So data cleaning is a huge thing that you need to do. So we will get rid of that when we do our coding example later. Okay, so for regression tasks, we have two basic questions we can ask. So first is our inference, which is basically how do our variables affect each other? So we have some dependent variable, and we want to know when we change this dependent variable, how is that affecting our outcome? So we can have very specific answers to how does each variable change graduation rate, for example. So when we're looking at our three plots on the bottom, we have three different variables we're looking at. So the first one on the far left is out-of-state tuition versus graduation rate. In the middle, we have room and board costs versus graduation rate, and on the right is student to faculty ratio. So when we're looking at relationships between these variables, we might say that the one on the left in the middle has somewhat of a linear relationship. We can see there's some kind of trend there, whereas the student to faculty ratio, we really don't see much of a trend because we have most of our student to faculty ratio falling between about 10 and 25. So there's really no trend that we wouldn't expect this to be a good predictor of graduation rate. So that is the inference part of how do our variables relate to each other. Then another question we can ask is the prediction. So once I make this model, how, if I had a new college we looked at, and let's say we've collected all the data for all the variables, but we don't know the graduation rate. Or let's say it's a new college and no one has graduated yet. So we know what the room and board costs and we know the student to faculty ratio, but we don't know what the graduation rate might be. So we could potentially make a model, so because we know how each variable is affecting our outcome, and then we would be able to predict what the graduation rate would be for this new college. So this is just a list of potential regression models that we're going to go through today. And so the big question is, how do you choose between these? When you have data and you either want to know how the variables relate to our outcome or predict a new school, how are we going to choose from these models? So the way we're going to work through this is on the scale of interpretable to flexible. So if you have a highly interpretable model, like we saw in the introduction, usually they're not as flexible. So we're going to get like linear regressions. So something very simple, but we can say exactly how much each predictor is affecting our outcome. Whereas if we have something more flexible, that's going to find all the little nuances in our data, that's going to be harder to tell exactly what each variable is contributing to our outcome. So we'll see later that those more flexible ones are better for prediction type tasks, and the interpretable ones are better for the inference. So we're going to start with just a simple linear regression. So throughout our talks here, we're going to have this star rating in the upper right corner for you to follow exactly the interpretability and the flexibility between these models. So starting at a very interpretable model, but highly inflexible. So the simple linear regression is just modeling one variable to the outcome. So just like you all have seen in algebra class, y equals mx plus b, we're just fitting a line to our data. That's it. So when we run a simple linear regression with one variable, we're going to get a slope and we're going to get a y-intercept. So this is just an example in R of what you might get out. So the coefficients we get for this model, if we run we want to model graduation rate as a function of room and board. Can I point here? So the intercept we get here is about 36%. So that means when we charge 0 for room and board, our graduation rate we would expect is about 36%. And then with each increase with each unit increase, and a unit here is $1,000 for room and board, we get an increase of about 6.6% in graduation rate. So this is a highly interpretable model because I can tell you exactly how room and board is affecting our graduation rate. But is it flexible? Not so much. So we plotted it here. So it goes on low flexibility, high interpretability.
All right. So how about other how about other independent variables like something like estimated book costs? So we basically extend our simple linear regression by adding these other independent variables in our model. You can see here how we just added another independent variable in terms of book costs, and you see that you can still get a super interpretable model out of our output in the coefficients, interpreted by adding unit increase of each individual independent variable to see its effect on graduation rate. So this is just a simple extension of the linear model. We gain a little bit of flexibility, but we might decrease some of our interpretability because we're adding more and more variables to the model. So just as an aside, our linear regression refers to linear in terms of the parameters. We can transform these independent variables in different ways and still use linear regression. So for example, if we had a graduation rate where we have our book cost, but then the square root of our student-faculty ratio, because we believe that's the correct interpretation for how student-faculty ratio would affect graduation rate. We may also include interaction terms, such as including out-of-state and room and board costs. We can add a lot of different variables, but at the same time, adding too many variables may lead to a flexible model, but we'll be at a risk of potentially overfitting, where we could have poor predictions on new data points and low interpretability, because if some of these variables don't contribute to the response, we want to get rid of them to improve our model fit. How might we try to do that? So just as a side, we're going to keep going back to this plot. We see how multiple regression, we have increased our flexibility, but perhaps at a cost of some interpretability. All right, so we're going to talk about selecting variables. We can try to reduce the number of variables that we have in our model to improve interpretability. There are many different ways to go about doing this. One basic way is something called subset selection, where you basically compare models with different numbers of variables. So for example, here, it's just stepping through, we have one model where we have just one variable, estimated book costs. We might compare it with a second model where we add the intermediate variable of student-faculty ratio. And then we might have a third model where we have only student-faculty ratio. You can still see how it sort of goes on from there. Another way you could try to select variables is by something called stepwise selection. So we might start with one model and add or decrease the number of independent variables at each different model. So again, you have this one basic model here where you have your estimated book costs. In your next model you want to compare, you add student-faculty ratio. Next time you might add the top 25% of your high school students, and then maybe you might step back again. So there are different ways to sort of implement these two different methods of subset selection that we'll step through with the code. Another method that you can do to try to reduce the dimensions of your parameters is basically to apply principal components analysis on your independent variables, and that's just something that we won't really address with our coding exercise. But we saw before when we were doing subset selection, we were trying to compare a lot of different variables and models at once. Maybe it would be too computationally intensive or too costly if you had a data set that had a lot of different independent variables, because you'd be choosing all the different combinations of every single independent variable that you would have. There are other ways you could try to select variables and shrink basically your coefficients, and this is called regularization. So there are two main methods to do this. They're called ridge regression and lasso regression. The way these work is by penalizing high coefficient values with some sort of tuning parameter. With ridge regression, the way that it works is that you shrink your coefficients towards 0 to basically decrease the size of your coefficients in your multiple linear regression model. Lasso does the same, where you shrink the regression coefficients, but at the same time, with the way that a penalty works, you can actually shrink some of the variables to 0 exactly. So it works sort of like subset selection. What this does is that it improves your prediction ability by reducing variance. It's less computational effort than subset selection because you're not going to try to compare all these different models. And in general, these are sort of fuzzy rules. You would try to use ridge regression when you think most of your variables might have some small effect. and you would try to use lasso when you think you have a few variables that have much stronger influence than your others. All right, so that just places it back in the same context as before, where when we do lasso or subset regression, we can increase our interpretability a little bit because we're reducing the variables. At the same time, we keep most of the flexibility as we have for multiple regression. All right, and this is probably my favorite topic. We want to try to move beyond linear regression. So what if we want to introduce more flexibility in our models for more complicated situations? So instead of having a line, your independent variables have different effects at different values. For example, we have here, again, it should be a we have student factor ratio and room and board costs. So we might try to fit different polynomials to your independent variables in your multiple regression. But what if there's some sort of discontinuous function where student faculty ratio doesn't really affect your graduation rate unless it gets to some high limit? So that's an example of this function here. How might you try to fit that in a regression model? One thing we try to do is something called Generalized Additive Models, or GAMs. It's generalized in the sense that you have functions of these independent variables. And what kind of function do you choose? There are a lot of different kinds with the way that different packages implement these models. It basically selects these functions for you, so you don't need to predetermine them yourself. It's additive in the sense that you're adding the contribution from each of these functions independently. So the example here is that in our model, our graduation rate is a function of book costs, a function of student faculty ratio, and you can also have different interactions in there. So with GAMs, we're increasing our flexibility at the cost of some interpretability. In sense of flexibility, we can find different functions of independent variables, including ones that you didn't think of ahead of time. And these non-linear fits may improve your prediction capability. But in terms of interpretability, you still are able to examine the effect of each independent variable on its response while holding other ones fixed because of this additive nature. But because you're having these functions of independent variables, what exactly would a sign of estimated book cost mean in reality? So that's one of the trade-offs of using GAMs. So because GAMs sort of sit in between this interpretability and flexibility curve, they're basically right in the middle of these, this plot.
All right, so we got one big gap to fill. So we need something that's highly flexible and low interpretability. And for that, we have our neural networks. So a neural network, so let's step back for a second. So multiple regression, we had adding still lots of different variables together that could be transformed in some way. For GAMs, we had a function of these variables. And for neural networks, we can basically use functions to get an output and then use another function on that output to get another output and do this throughout a network, and those are going to be your layers. So here's a very basic neural net. So here we have our input in yellow and our output in pink, and we have no hidden layers. So we forgot to label one of the nodes. The top node should be books, and the bottom node is room and board cost. So when you're inputting things to your neural net, each of these nodes gets what that variable is for each individual sample that you have. So here would be a single university you input to the network, and then it calculates these beta values, which is the same as you would think in our regression models that we had before. So it's calculating these betas, or our weights, and then we get some kind of output. So with this very, very basic neural network, this is just the same as the regression model we had before. Nothing's different. We would get the same exact output. What's different when we get to neural networks is we add an activation function to this final node. So we transform our output in some way. So when we make this a little bit more complicated, we have our hidden layers in the middle. So the layers are the actual nodes and not the connections between the nodes. So here we have two hidden layers with 3 nodes in the first and 2 nodes in the second. And so what would happen is we input each individual university's values into this network. It calculates weights for each of those hidden layers. So it would go to the first layer, it would calculate its weights, and then it has some activation function. So it's kind of like the GAMs. We have some function on that output value, and then we take that output and and insert it into another function, which we don't know. This is kind of a black box. The computer figures this out. And we have yet another activation function, and then we get our final graduation rate prediction. So this is highly flexible because it's finding all the little nuances in the data, because we're inputting each university at a time, and it's fine-tuning its parameters to each university as we insert them into the model. But it's highly uninterpretable because we have no idea the effect of a single variable that we started with. We can't say exactly how much the estimated book cost is affecting our outcome of graduation rate. We have no clue. So when we're building neural networks, we have a few questions that we need to answer, like how many layers do we need? So here we have 2 layers. How many nodes in each layer? That can affect our outcome. And how do we choose our activation function? So what kind of function are we going to use to transform our data? And there really is no rule for following for this. There's general rules of thumb where a single layer is generally good enough. And we never want more nodes than we have input nodes. So we wouldn't want a lot of hidden layers in the middle because that would be way overfitting our data, and there's no way that would be generalizable. And we also don't want more nodes in our hidden layers than we have in our input because that also would be way overfitting. So this is kind of comes with the art, like Andrew was talking about, how to actually fit these models so we're not overfitting, but we get good prediction values. So this is basically what I just said. So we have greater flexibility, but basically no interpretability. So now we can use we can use our neural networks for prediction challenges. So we will stick neural networks in the high flexibility, low interpretability.
So hopefully that helps you put a bunch of different regression methods into context. We went through a few different types of regression where we talked about simple linear regression and multiple regression. These might be really good for inference problems. Same with Lauziere and rich regression because of the ways that they work to reduce your variables and increase your interpretability. On the other hand, things like generalized additive models or GAMs, these are adding linear or nonlinear functions of your explanatory variables or your independent variables. They are more flexible, but at the same time, you might lose some interpretability. And as Theresa mentioned, with feed-forward neural networks, you can find very, very complicated functions of your independent variables to estimate some relationship, but you definitely lose interpretability, and you might be worse at inference. So these first 2 might be better for inference tasks, while the latter 2 might be better for predictive tasks. Are there any questions? All right, we have hopefully something that will lead to some fruitful discussions among 2 groups. You might try to think about what sort of data you have in your research, and if it's a question you could try to answer a regression approach. What method might you want to try to apply to your data? Is interpretability more important for you? Is prediction more important for you? How would you choose the different features you might use in your regression? And whether or not you would choose a more flexible model. All right, discuss.
Okay. So again, these are the steps for downloading the notebooks, right? We're going to leave it here for a second before we pass it off. This link as well, like this information was in the go.umd/sml link that you guys checked in the beginning. And again, if you guys have not filled out the go.umd/sml all caps, could you please do that? This information is also on that survey, and that information is important for the Combine program so that we can continue to host powerful workshops such as this one here today. And just for clarity as well, since obviously it doesn't really make sense for us to go through both notebooks simultaneously, we're going to be putting the Python notebook on the screen. However, the R notebook is very similar as well. And so you're going to see the same function. So if you're more of an R user, you're welcome to download and look at that on your own. But if you want to kind of run the code step by step with us, we'll be doing the Python one. With the R one, it takes a little bit more time to get set up. As you can see, there are more steps. So we're just going to give you guys a few minutes to kind of pick which one you want. It's an important decision. And then get the notebook opened up as well. And then after a minute, when each of you have done that, we're going to pass it on to Hadi, who's going to start walking through the code for the regression tasks with everyone.
All right. Does everybody have, at least people who use Python, do you see this in your screens? This is the notebook. So after opening the notebook, so here, because we have access, in the top corner says editing, but for you it's gonna say view only. Because of that, after opening the notebook, you should go to File and save a copy in Drive. I'm not gonna do it, but you should do it. And then this is gonna save a copy just for you in your Google Drive, so that you can open that and edit it. And the purpose of this is that you're gonna edit your code and just experiment and run it and see what happens. But you can't edit this one. So. All right, first of all, make sure that you do that if you haven't done already, and we're gonna go through the code. All right, so this is really not working. Is this working? Anyway, I'll just hold it. So, all right. This is first of all, here you're gonna import some modules that you're gonna use. This is just a Python thing, and we have some comments that explains what all these things do. And then this is the part where you load the data. This data is available online, and this is a fairly famous data that is from the book that we cited, like the statistics book. And then, if you run it, I'm not going to run it for you because we want you to run the code and see the result. So here, data.head, this is a pandas data frame. It will describe the data, kind of, give some information about what the data is about. And describe will give you some information about the mean, variance, and things like that in your data. And then this is the part that you don't really have to look at. This is the ugly truth that your data is always noisy. You have to clean it up. So we did it for you. And then, okay, here's the regression section. This is where you're gonna play around with the code. So first of all, after cleaning the data, we're gonna have this function, which is process data. It gives a pandas data frame in, and it kind of makes a train test split. And the purpose here is that you have a training data set and all right, yeah, are you running or am I too fast? All right, if I'm too fast, just yell at me and stop me. All right, so here, this is just a function that processes the data for you. It's still not important for you to understand what this is about. But here you see that we have a bunch of those models that Hao and Theresa described: linear regression, ridge regression, lasso, and neural network. You're gonna run these and see the results for yourselves. So in each of these sections, there's a part that you actually build a model. Here you train a model, and just let me mention that in Python and R, a lot of these standardized models are just available to load. You don't actually have to do more than that. So for example here, if you want to use a linear regression model, there is this scikit-learn package that you can import and train just as easy as this. And this line here is for model evaluation that you're gonna see as you progress further to more complicated models, you're gonna get better and better scores. So I'm not gonna go into details of all of this because that's what you're gonna do in the coding section. But there's a bunch of visualizations and some plots that you're gonna see the purpose of those. And yeah, so far from linear regression, ridge regression, and lasso, these are mostly simply you import the model here. Linear regression was imported, you just fit it, or ridge regression, it's imported here. But here when we go to the feed forward part, so here you don't need to really understand what this is about. This is just us building a simple neural network for you to just run and train your neural network. Here you don't need to understand the details. But what we're going to ask you to do is that play around with your neural network, like add more layers by uncommenting these, or change the number of neurons in each layer, and then run these again to actually see how it affects your outcome. And that's it. That's it for this part. So I'm going to let you to actually run through the code, and we're going to walk around, and if you have any questions, we're going to just raise your hands. We can answer. All right, everyone. Now it's time to go to the second half of the lectures. Now we're going to talk about classification. So, does anyone want to define what classification is? What do you think when you hear the term classification? What is class and what is ification? Okay. So, well, in our data set, in our example data set, we can choose to say that, we say colleges that have graduation rate greater than 65%, we can call them colleges with high graduation rate, or high colleges for short. And then low colleges, just like that. And now we have two classes. Instead of continuous numbers, we have colleges that are high or low, based on the thing we just defined. Now our goal is to build a model that, given the data, is able to predict whether a college will be high or low. So, if you look at this plot, the blue dots, or triangles, they correspond to high colleges, and the red ones are low colleges. And x-axis is out-of-state tuition, and y is percentage of alumni who donate. You can see kind of that there is a structure here. The colleges that are high tend to go to upper right part of this plot, and the colleges that are low tend to go to the other side, which you can see here. So there is some structure. We want a model to learn this. How we do that? But first of all, before actually talking about classification modeling, we're going to talk about how we can evaluate these models. So first of all, here's what happens. When you have a classification task, you get your data, you have input variables x's, you have output variables, which are now labels. Here we have y's. These are actually either highs or lows, and x's are just a bunch of numbers. You break this data set into two parts, test part and training part. You train the model on using the training data set, and then once you're done with training the model, you feed your test data through the model, and the model predicts some labels. These are y-hats here. And then we evaluate by comparing y-hats to the true labels, which are y's. But how do we do this? Does anyone have any suggestions? So let's say my predicted labels here are, like there's 5 colleges, and the actual labels are high, high, low, low, high. And my prediction is high, 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 high. All of them are high. How do I evaluate this model? So I have this, my model learned something. Did it learn a useful thing or did it not? What are the ways of evaluating the output? So, first thing that comes to mind is accuracy. And accuracy stands for the percentage of output labels that my model got right. And the example I told you about is actually 3 out of 5, which is 60%. So there's other definitions such as true positive, false positive. What are these? When you have a classification model, you need to know these definitions. For example, a true positive is something that the label actually was high, and my model correctly predicted high. A false positive is that when a college was really low, but my model falsely classified that as high. So here, positive or negative stands for high or low. It's what my model gives me, but true and false stands for whether the prediction was correct or incorrect. So you get the idea, right? Based on these things, like true positive and false positive and all the other ones, we can define other measures of success. Accuracy was the most obvious one, but we can define precision, such as that is true positives divided by true positives plus false positives. And to give you an example why sometimes precision is preferred over other measures such as accuracy, an example would be, let's say I want to build a model that predicts YouTube videos. It actually is a YouTube video recommender. Here, a positive result is a good recommendation. A video that is interesting and my model correctly identifies that as interesting. And a false positive here would be a boring video that my model incorrectly labels as interesting. So here I don't want false, I want to minimize false positives. That's why I want to maximize precision. There's another measure, it's called recall. And I'm not going to go into details of this because it's on the slides, you can actually look at them later, but here your goal is to minimize false negatives. And it's important for like some examples such as rare event detection, such as cancer detection, because a false negative means that the patient actually had cancer, but your model falsely didn't detect it, it missed it. So it's very dangerous. So for these models, you want to look at recall instead of precision or accuracy. This is a summary of what I just said. All right, now let's talk about the actual modeling. The simplest classifier, which is still very powerful and popular, it's logistic regression. I want you to look at this data set for like 10 seconds and really absorb what do you see there? This is a fake data. It's one-dimensional. There is an input variable x, and there is the labels high and low, just like our example. So you see some structure here, right? If the x value is above 0, then your label is high. If x is below 0, your label is low. And how do you build a model that detects this? Think for 10 seconds and recommend something. Like, how do you go about this? All right. Any suggestions? Yeah.
Wait, you're saying how to model this one in particular?
Yeah. No. This particular example.
A step function.
A step function. Exactly. Thank you. So, a step function. First of all, if you want to do a linear model, it would look like this, right? You would have a linear fit that does a poor job of classifying. It misses a lot of data points. But if you had a step function at around x equals 0, and you would say, oh, anything below x is low, x equals 0 is low, and above 0 is high, then you can actually have a very, very good model. And what is the best continuous approximation of a step function? That's the sigmoid. So this is logistic regression, basically. You have a linear part here. This is the line. But then you put it through this sigmoid function. And it actually captures your data beautifully. But this was very simple. The idea is the same for high-dimensional data. All right. Now, our first question was that we wanted to build a model that has good performance, high accuracy. But the second question we can ask is that how do these variables contribute to the classifier's decision? So let's say your classifier says a college is high or a college is low. Which variable did the classifier look at the most? Was it the number of students, or was it the tuition cost? Which one of these is playing a bigger role in the classification decision? It turns out we can actually study this by using simple models such as logistic regression. So going back to one of these plots, here again we have this percentage of alumni who donate versus graduation rate scatter plot. And these are high versus low colleges. That's our threshold is there. And if we fit a linear model, it looks like this. So basically the whole point of this plot, having this plot here, is that there is a relationship between percentage of alumni who donate versus graduation rate. You can see that as you increase the percentage of alumni who donate, your graduation rate also increases. So we are curious if our logistic regression model also captures this. How do we do this? Oh, and this is just the same thing, but two different variables. Like you see that the books doesn't matter, the percentage of alumni matters. How do we do this? So this is a logistic regression model. There is y. There's coefficients that are multiplied to your input variables. We can actually, turns out, after fitting the model, we can look at those fitted coefficients. In here, those are the betas. And if a beta has a large absolute value, it turns out the coefficient, the corresponding variable, plays a large role, important role, in the output of the classifier. You can see that here. If actually, like in the extreme ends, if let's say if beta out of state is infinitely large, then small changes in the input value of out of state, x out of state, will change y drastically. And if beta books is 0, it doesn't matter whether you change x books or not. It's not going to matter for the output of the model. So looking at these coefficients will help you determine which of these variables were important. This is what we did, and you're gonna reproduce this plot in the code as well. So if you actually look at, if you fit a logistic regression model to the data, and you look at the coefficients, this is how they look like. And just to re-emphasize, for example, the out-of-state coefficient is large. You can kind of see that relationship between that and graduation rate, but the books coefficient is small, and you don't see that in the plot there, in the right corner. All right, so that was logistic regression, and that's where it fits. It's high interpretability, but low flexibility.
All right, so another method you can use for classification is called support vector machine, or SVM. So when you have a clear distinction between your categories, so this is a really simple example, but let's say you have all these blue dots and these red squares. You can draw your line between them in a bunch of different ways. You can have one kind of at this angle, you can have one at this angle, but SVM actually finds a boundary based on the maximum margin between the two closest points. So you see here, this line is drawn, so you have the maximum space between this blue dot and these red squares. This is really helpful because if you are doing this on your training set and then you are adding additional test data, you have more of a probability that your data is going to end up in the right spot because you have this boundary or this margin of error that you could use. This technique is also good because you can use it for multiple predictors. So in this example, we just have an X1 and an X2 predictor, but you can have more dimensions, and instead of this just being a line, it could be a two-dimensional plane, for example. And one thing to note when you compare this with the regression is that regression is more sensitive to outliers. So in this example, most of our blues, like high colleges, are clustered here. We have this one outlier over here. And so regression would take that into account and change the angle of the line here. SVM may misclassify this one, but it will keep this boundary. So as you have more data points that aren't outliers like this one, you're still more likely to classify them correctly. And our interpretability versus flexibility graph, it's about in the middle. So you have flexibility and you have interpretability. Another method are called decision trees. So these use multiple tests of your observations or predictor variables and then make conclusions based on all those tests. So in this example, we have colleges plotted with out-of-state tuition versus the percentage of their class that were in the top 10% of high school. And so you'll notice if you go at 66% being in the top 10%, all of these colleges over here are these high graduation rate colleges. So our decision tree can first ask, is the percentage above 66%? If the answer is yes, we can go ahead and say, oh, it's just a high graduation rate college. If the answer is no, we have all this mix of things over here. So we need another question to disambiguate the class. So we can ask here if the tuition is greater than 10,000. And you see there tends to be more of these high graduation rate blue arrows above that and more of the low graduation rate below. So then we can classify that. But you'll notice that there is a lot of overlap. And so you might have a decision tree that's only not super accurate. So in order to get around that, you could use a random forest, which is taking the output of a bunch of decision trees and combining it. So you could either have different cutoff points with your same predictor variables, or you could have decision trees that are using different predictor variables. And all of the answers from the decision trees will come together and give you your final answer. And on our graph, decision trees are a little bit more interpretable than SVMs, but they have a little bit less flexibility. When you go to random forests, you have a bit more flexibility because you have the input from all of these trees coming together, but you have a little bit less interpretability because all the different trees that are underlying your model have different outputs that you may or may not know about. And we talked about feed-forward neural networks for regression. They're also applicable for classification. And we went into detail about that, how you can have different numbers of layers and different numbers of nodes. And so one fun resource that we found when we were putting this together is this website, playground.tensorflow.org. And so you can actually go to that website and it has a representation of the different inputs and nodes, and you can see how well it does on the classification tasks if you increase the number of nodes or increase the number of hidden layers. And it's a fun way to visualize that.
So just one insight that we would like you to remember about neural networks is that they are universal function approximators. And what that means is that if you have data X, and if you want to map them to output Y, and you don't care about what F is, you just want to find some F that, optimizes some performance, and Y equals F of X, then neural networks can be useful. And there's this interesting theoretical result, the paper that we've cited there. It's a little bit mathy, but it's interesting if you want to look at it, that proves this result, that feed-forward neural networks, multiple layers, and nonlinearities, such as sigmoids, they can achieve this universal function approximation. But there's this very interesting resource, the visual proof, the other link, that goes through a really long, interesting article that visually proves that neural networks can approximate any function to desired accuracy. And I suggest if you're considering using neural networks for your research, go take a look at it. And you will learn, you will know that neural networks are good function approximators, and you will feel powerful, because knowledge is power. Okay, so that's that. This is the last slide. You're going to make this plot in the code. You're going to see that for this data set, the different models, this is their performance using the measures that we defined: accuracy, precision, and recall. And for this particular data set, the neural net doesn't really outperform the other models by that much because the data set is small. So it's not worth the headache. And then one thing about the caveats of throwing deep neural networks at everything is this example. So if you think that deep networks are just neural nets are going to solve all your problems, that's probably not true, because this paper on the left came out 2 years ago in 2018. They use a deep neural network to predict aftershock patterns. Their model is very large with 13,000 parameters. But then a year later, this other paper came out on the right, and they showed that this logistic regression that we learned about, it can actually achieve the same performance with only 2 parameters. A single neuron logistic regression can achieve performance of a 13,000 parameter deep neural network. So these kinds of results are not rare, so be careful. All right, now it's time for the next discussion. You can talk about your own research and see that if you can, if there is a classification problem in your research that you can use one of these models for. All right, so classification is also a bunch of different sections, subsections. First of all, you're gonna run this code. There is some, plotting functions that we wrote. You're gonna run these and they're gonna produce some plots that is interesting. Just look at them, nothing more. Then here, you're gonna train your logistic regression model. And after training it, you're going to evaluate it, looking at the accuracy, precision, recall, and all of that. And this part is the second question, the interpretation of logistic regression model. The plot that had the coefficient importance thing, the plot is going to be reproduced here. And then here we have a function. This is another one that processes data, not important. But this fit classification model, this gets in data, the data of pandas data frame, and you choose your model. You can be logistic regression, SVM, tree, or random forest. And then based on your choice, it goes into the function, it just trains your model, it returns the classifier object. And here's how you can use it. You can just train 4 different classifiers on the same data, and you'll see the results. There is another function that evaluates. You just pass the classifier in. This is not a trained classifier. It has been trained on your trained data. And then you pass in the data again, and it kind of prints out some information about how your model did. Like it's about evaluating your model. And here you'll see, after running this, you'll see some results about that. And then you'll plot the results. Again, you have the same feed-forward model, but there's some slight differences here. For example, the softmax here. You have a model, there's 2 hidden layers, 20 neurons each, and the output layer has a softmax nonlinearity. You don't need to worry about this. I'm mentioning this is because now it's a different kind of model. The other one was for regression. This is for classification. So the output of this model should be a probability over which class your sample is from. Anyway, that's not really important for now. But this, like, the rest is more or less the same. There is also some sort of like processing stuff. If you wanna work with Keras, you need to actually. So our output data here is the y vector is bunch of zeros and ones. Zeros correspond to low and ones correspond to high. And then this function to categorical, it actually just processes that in a way that Keras uses. So don't worry about that. Here you train your model. You provided the training input data and the training output data. Just train it. You can evaluate it on the test data. This is all test. and then you can plot the history of the training. You're going to see that the accuracy after a few epochs just goes up. And then here you can just print out some more evaluation metrics. And then what you do here is just, so far the fit results, this guy here, it had information about our fits with other models, non-neural network models. Here it just concatenates the new results to that, and then you will plot the final thing. This is going to be the bar plot that we had on the last slide. And you'll plot it here. And there's this bonus part if you want to run it. This kind of is trying to emphasize the dependence of the kind of randomness that goes into these complex models. For example, I'm not going to define this, but maybe I'm going to mention it. Logistic regression and SVM. One of the reasons why those models are interesting is that to some people, it depends depending on what you want to get out of them, is that they're convex optimization. No matter what initial parameters you start for your models, you're going to converge to the same answer. And some people, especially people working in sciences like neuroscience, biology, they might care about this. They want to, it might freak them out if you run the model with a different seed, you might get a different answer, and they don't like that. So you do this with 10 different seeds, and you're going to see that the error bar is going to be an indicator that neural networks and random forests and decision trees, they are non-convex, and logistic regression and SVMs are convex, if you care about that. So that's it. Just run through them, and if you have questions, raise your hand. All right, just before people leave, I'm just gonna show you some more slides about maybe the take-home remarks here. One thing is we wanted to actually emphasize on that there's this link between statistics and machine learning that people, don't talk about much, but it's pretty much true. Lots of machine learning models are just, you can call them statistical learning, it's the same thing. And this tweet kind of shows the same thing. So this guy, David Cicillo, is a computational neuroscientist at Google. He says, "Today is the first day I have ever used logistic regression." And Surya Ganguly is a computational neuroscience professor at Stanford. He says, "Oh, you mean a no hidden layer deep neural network with only one sigmoidal output neuron? Why didn't you say so instead of using obscure statistical jargon like logistic regression?" This is the state of the community. I'm not going to comment more, but actually that's technically true though. I mean, logistic regression is just a no hidden layer neural network with a nonlinearity. All right, and this is basically what I said. Next time someone mentions artificial intelligence, think advanced curve fitting, for the most part, especially if they're a company from Silicon Valley. But then they're useful if you have a task that is anything that is just y equals f of x, and you have a bunch of data, you can learn f from data. And the last thing, so here we didn't have time to go into advanced models, but it's not confirmed yet, but there's a possibility that we can have a week-long workshop about these topics. And we're going to ask you in the post-workshop survey about which of these topics you might be interested in learning more, so that we can design a workshop and just go through into more details. Thank you.